Hi, I'm Kirwan Bonifas.
And I'm Farabaugh.
And our project was the stability dynamics of a penny farthing. Now, what is a penny farthing, you may ask? Well, the same as an ordinary bicycle or a high-wheeler. It's just this bicycle here with a huge front wheel. It's really similar to the bicycle that you may have at home with two key differences. One is direct drive gearing. Since high-wheelers were made before gear ratios were fully worked out and before belts and chains were worked into bicycles, there's direct drive gearing. All this means is that the pedals are connected directly and fixed to the front wheel. For the user and in terms of stability, there is a torque added to the front wheel by having the pedals connected directly to it that causes wobble much similar to the speed wobble that you would see at high speeds on a regular bicycle. The user must constantly correct for this, dampening it with turning the handlebars. In addition, the user has a much higher and more forward center of mass, meaning that the user can actually tip over the front of the bicycle like a unicycle, and they can't lean quite as far as you would in a regular bicycle. Inputs are the same as a regular bicycle: pedals to accelerate and decelerate, handlebars to turn, and throwing your arm out to change your inertia matrix.
The frames of the system are the wheel frame, shown in red, the fork frame, shown in green, and the saddle frame, shown in blue. All of these frames have the same orientation and are merely located at and slaved to different parts of the bicycle. The wheel frame rotates constantly about its z-axis out of the screen as the bicycle moves, rotates about its x-axis vertically as the user steers, and about its y-axis horizontally as the user leans side to side. The fork frame is much the same as the wheel frame, except that it does not constantly rotate about its z-axis, only doing so when the user begins to fall over the front of the bike. Steering is done about the x-axis of the fork frame with respect to the saddle frame, which does not move with respect to the bike.
For equations of motion, we are considering things from the user's frame. The equations of motion that the user is going to be able to sense are the angular acceleration and the change in Euler rates from the saddle frame. Since our system acts much like an upside-down pendulum, especially as far as our lean angle is concerned, a stable lean angle is one where the force due to the user falling over is equal to the force due to centripetal acceleration. Thus, theta is equal to the arctangent of v squared over g times r, or centripetal acceleration mixed in with the gravitational acceleration term.
The physical outputs of the system, all with respect to the saddle frame, are the forward speed of the bicycle and the rider, the lean angle theta and its rate of change, the tilt angle psi and its rate of change, and the turn angle phi and its rate of change. The lean angle is the angle side to side that the user leans during turns. Tilt angle psi only comes into play when the user begins to fall over the front wheel of the bicycle, and the turn angle phi is the angle of the handlebars when the user steers. All of these outputs and measurements are continuously taken by the rider and dynamically changed. This means the system is continuous as opposed to discrete.
As far as control is concerned, the control law implemented in this system is somewhere between proportional and PID. This is due to the uncertainty about how exactly the human brain can figure out things exactly right. Think about when you're trying to correct your imbalance on a regular bicycle and you throw your arm out to change your inertia matrix. Well, you're probably going to overcorrect. Or if you turn your wheel, again, probably going to overcorrect. Both of these things are even amplified on a high-wheeler, hence an overcorrecting step function that takes a while to fully restabilize. Our control law block diagram can be seen above with an initial input and a human proportional control, running through the system dynamics, i.e. the tilt, turn, lean, angular acceleration, all tracked by the human and given feedback back into the human's control to change the system dynamics in the way that they wish.
In summary, our system of the penny farthing operates under the governing equations of the general torque applied to the front wheel and the turn rate and radius to compensate for gravity. The inputs of pedal force, steering angle, and position of the center of mass control the outputs of the bicycle speed, body rotation angles, and front wheel wobble. All outputs are measured and given human feedback in a continuous loop using a simple proportional control law. The frames involved are the saddle frame, fork frame, and front wheel frame, with all measurements and observations being made by the rider from the saddle frame.
Thank you very much, and happy riding!